Hi, my name is Hee-Seung from Yonsei University. Today, I'll present my work about speeding up inference with user simulators through policy modulation. This work was done in collaboration with Electronics and Telecommunications Research Institute and Naver AI Lab. This talk deals with how to infer users' invisible characteristics from their observed behavior. Nowadays, it is very easy to collect user behavior data from anywhere on any device. For example, while a user is surfing the internet, we can record every movement of the user's mouse cursor, including which button was pressed and how long it took. With this rich daily data, what we try to do is to identify the user's characteristics such as cognitive capabilities or intrinsic rewards, which are usually difficult to measure. In the recent decade, with the emerging technologies such as deep reinforcement learning, there have been significant advances in the study of cognitive models that simulate user behavior. Within the simulator, a user's cognitive process is mathematically modeled, and characteristics of the simulated users are usually reflected in this model. Then, we can discover the optimal action policy of the user through reinforcement learning. As a result, with recent cognitive models, we can now reproduce user behavior from given characteristics in various task domains. These user simulators can be utilized to infer an actual user's characteristics. Let's say we observed the behavioral data from a user. Using the user simulator, we can simulate user behaviors that are corresponding to different user characteristics. What we need to do is to find the user characteristics that reproduce the most similar behavior to the observed behavior. Within this simple but powerful inference method, the biggest challenge so far is the computational cost of simulating user behaviors under different characteristics. With previous cognitive models, when the user characteristics are changed, the corresponding action policy should be newly obtained through reinforcement learning. In order to solve this inefficiency problem, in this study, we present a method of generalizing the action policy of the user simulator so that the simulated behavior can be immediately reflect variations in user characteristics. In previous user simulators, the action policy has been trained under the single fixed user characteristics. For example, the action policy can be implemented by deep queue network which predict the optimal action from a given task state. Until now, the mapping between the task state and actions was implemented for each different user characteristics. Our approach is to implement an action policy that can effectively modulate this mapping according to given user characteristics. We presented a modulated queue network structure, which is based on a recent technique of conditioning neural networks. In this structure, the latent parameters extracted from user characteristics are concatenated to every intermediate output of the neural layers and eventually affect the overall mapping. With this policy modulation technique, the inference process no longer requires the policy reoptimization to simulate different user behaviors. An inference process that would have taken thousands of hours so far can be done in a matter of hours with our method. We evaluated our inference process based on the latest point-and-click model, which can simulate the behavior of a user clicking a moving target on screen by manipulating a mouse cursor. In this model, simulated behavior can reflect the user's cognitive capabilities and reward formulation. We investigated whether it is possible to infer the two types of characteristics with our method. For this, we built a point-and-click behavior dataset from 20 participants. First, by conducting 3 different cognitive experiments, we measured baseline values of cognitive capabilities of each participant. And we collected their point-and-click behavior under 3 different instructions that control the degree of their speed accuracy bias. We trained a point-and-click model to be generalized over various user characteristics through policy modulation. After the training, we were able to investigate how the simulated behavior changes according to the variations in the user's reward formulation or cognitive capabilities by only using a single model. For example, if a simulated user is rewarded more by a successful click than by fast completion, the model changes their behavior to wait more for the correct click. On the other hand, we can see how the behavioral strategy can be affected when there is a variation in simulated users' vision noise. The important point is that these changes in behavioral strategy were achieved from one generalized user simulator. Using this trained model, we inferred the user characteristics from the behavior of actual participants. This can be achieved by finding the simulated user's characteristics that best reproduce the observed behavior. We first examined how the three different instructions changed the participant reward formulation, which consists of reward weights corresponding to click success, motor effort, and completion time. With the inferred reward weights, we can now explain the changes in participants' behavior strategy based on the quantitative values. For example, when given an instruction that emphasizes accuracy, participants performed a task with a high reward weight on successful click. On the other hand, when given instructions that emphasizes speed, participants gave a high weight on completion time, and they lowered the weight on motor effort, which means that they were willing to take more effort to perform a task. Finally, we attempted to infer the cognitive capabilities of each participant. Among the three cognitive capabilities, we succeeded in inferring the baseline values of vision noise and internal clock precision, and this was achieved by only using their point-and-click behavior. So far, no attempt has been made to infer the capabilities of individual users from their behavior due to the computational costs of the inference process. Our method makes it possible to infer individual users' characteristics by significantly reducing the cost. I'd like to conclude this talk by saying that these inference techniques will be a powerful method for providing personalized user interfaces in the future. Thank you for the listening.